In this video, we're going to take a look at finding the volume between a hemisphere and a cone, which has been born out from that sphere. It turns out we can't just take the difference, geometry formulas, between that hemisphere and the cone because there's a curved top. So we have to use three-dimensional, that is vector or multivariable calculus. That's coming at you today on High Peak Education. Thank you for taking a look at our video. I look forward to getting into this. Let's not delay it all. Let's get right into the problem.
My question is this: what it threw me off, it was that 4 in front of the square root of x to the 2 and plus y to the 2 for the cone, for the C equation. And that's where I'm like, where did I get that freaking arctan 1/4? Where did it came from?
Yeah, okay, so let's take a look at it. It says find the volume of the solid that lies within the sphere, x squared plus y squared plus z squared equals 36, above the xy plane, and outside the cone, z equals 4 square root of x squared plus y squared. Okay, so first of all, one thing I was going to recommend, and this solution doesn't even sort of have it, is I was going to recommend still like a sketch, okay?
I think the one we use is the CalPlot 2D.
Okay, yeah, like I said, I think that one's a little more popular. Okay, so let's go ahead and just use that one. An implicit surface. So the equation's going to be x squared plus y squared plus z squared equals 36, right? Okay, let's see. And I want to plot this between plus and minus 6 for each x, y, and z. Okay. Woo. There we go. Okay, so I've got the sphere there first. It's 4 square root of x squared plus y squared. 4 square root of x squared plus y squared. 4 square root of x squared plus y squared. So one of the things I did is I toggled off the faces. I used the option on there, which is the letter F. So I toggled off the faces, the colored faces. So it's just kind of like an X-ray view, kind of a wired view. We've got the, let's see, so the z-axis goes up into the cone. Hopefully you can see that right here. Here's the z-axis, and there's the positive y-axis. And that means the x-axis goes out this way. Okay, all right. So what we want is, let's see, it says, find the volume of the solid that lies within the sphere above the xy plane, but then outside the cone. So basically, anything inside this cone, we're gonna sort of cancel out. So imagine that this kind of comes down like this, more or less. Again, somewhat of an X-ray view. It's none here. Okay, so none inside that cone. So it's kind of like boring a what would you call it? Like boring a conical hole in a sphere, okay? And by the way, like, you can't just, I mean, here's what a lot of people have said to me. Oh, Professor Culette, can't you just take the volume of a sphere and then subtract the volume of a cone? That won't work. The reason that won't work is because the top here is also curved. Do you see that? So you really have to do this sort of using the 3D calculus stuff, right? Because especially this top here, so it's sort of a curved top on the spherical surface. Okay? Okay. So that's the idea. So you can't just, you know, can't just do simple geometry formulas. Okay, so that won't work. Presumably, since we have a sphere and a cone, I'm thinking that spherical coordinates is going to be our friend. Okay? Definitely. Because if you were to try to do this in Cartesian, like, it'd be lots of square roots and lots of stuff like that. Plus, given what we've got here, notice that x squared plus y squared plus z squared is like rho squared equals 36 is the sphere. Z equals 4 square root of r squared would be cylindrical. Whoops, sorry. Okay. But, so that'd be 4r. But notice that's not going to be the cone in this case because we're not in cylindrical, we're in spherical. In one of our last sessions, yeah. So these are the equations for spherical. If you want like r squared, now notice r is still kind of harkens back to cylindrical, right? So it turns out you can get this r in terms of the other things. So r squared would be rho squared sine squared phi. So going back to here, if x squared plus y squared equals r squared can be written as rho squared sine of phi squared and the square root of that. So I think that's going to be useful. So that means z equals 4 rho sine phi. See that? So that's how they came up with this part right here, by the way. Do you see how I came up with this 4 rho sine phi? Then the question is, what's the z? Let me go back to here. What's the z coordinate? Well, z is rho cosine phi. So that's how you get this z coordinate. Because remember, we don't want z in there. We want to get rid of all x's and y's and z's and get all rho.
And use the
Right, so we're going to get rho. We're going to get rho and theta and phi, right? This is probably the hardest part because this right here is a relationship for the cone surface. So if it's a relationship for the cone surface, rho cosine phi equals 4 rho sine phi. Divide out the rows, okay? And then sine over cosine is tangent. Remember your trigonometric identities, right? Tan of phi is equal to sine phi over cosine phi. So that's what they used here. So then, notice that they've got tan phi equals 1/4. Now let's have a think about what that really means. Remember we said last session that when you consider a cone, so imagine this is the z-axis, right? And remember, this z-axis is just like this z-axis right here, right? Remember, phi here is it's curved. It's the declination angle, right? So declination means, how far down of an angle below straight up. It should make sense if we have a cone surface is defined by you sweep around the azimuthal angle, that's theta, but that the declination angle is staying constant. We did discuss that in the previous session. So the reason I'm bringing that to your attention again is it doesn't surprise me too much that we get tan of phi equals 1/4. Because if you think about it, that means phi is equal to a constant on the cone, which is what we expect, right? Because if you think about it, there's a certain angle, phi, and that defines the cone. Everywhere on the cone. At least on the outside surface of the cone. Don't worry about the top cap yet. We'll get to that. Okay? But anyway, just for the cone, that's what you have right here. Now, by the way, tan phi equals 1/4. I mean, so that's not going to be a nice value from the unit circle. It's just whatever it is, right? So if tan phi is 1/4, you can imagine that. So we know tangents like opposite over adjacent. It'd be a right triangle more or less like this. So if this is phi, it's phi. Then this is 1 and this is 4. Right? Because that's how we calculate tangent. So that's the basic idea. So now that we have that, we say, okay, then we can just say phi is arctan. That's the inverse tan of 1/4. Because that just follows from this equation. Because remember, we want to have some idea of phi for its bounds. If this is the z-axis here, so again, this is the z-axis. And remember, this is how we rotate down in terms of phi, right? We rotate down from the z-axis. You got to think about this three-dimensionally, right? This right here would be the phi minimum. Because if you think about it, let's see. Yeah, we're not going to take any volume from in here. So that's the minimum value of phi. But notice, oh, and by the way, I realized there's one other thing I should have done. I apologize for this, but remember, this only is above the xy plane. So I realized I forgot to do that. So what I should have done is I should have done this. What I'm trying to say is this is like sort of behind. So what I'm trying to say is this phi rotates down to the xy plane. But when it rotates down to the xy plane, then phi max should equal pi over 2. You see how I got that?
Yes.
Okay. So I think that's how they're getting these for the bounds. Arctan of 1/4, because that's all. This right here is on the cone edge. And then this right here is at the xy plane.
Example, if my cone equation would be c equal 8 the square root of x to the power of 2 plus y to the power of 2, right?
Yeah, right here in the first place, yeah.
So then my tangent would be
yes,
1
exactly.
over 8?
Yep. Inverse tangent of 1/4.
Inverse.
Okay. Let's think about what that looks like. So, you know, inverse tangent of 1/4, we could put that in the calculator, right? If making sure the calculator's in radian mode. Okay, so if we do inverse tangent of 1/4, let's see how many radians that is. That's about 0.245 radians. So it's about 0.245 radian. And by the way, 0.245 radians, you could take that, if you want to get that in degrees, you would multiply by 180 and divide by pi. So you multiply by 180 over pi. So we're just trying to get this as a ballpark. So it's about 14 degrees. So if you think about it, take a look at this diagram. Does this seem to be about 14 degrees right here? Yeah, about 14 degrees. You can kind of tell, right? 14 degrees right here. Whoop.
Yep.
14 degrees. Now the reason I bring that to your attention is because originally, when I was looking at this tangent value, I thought, okay, that's tangent of a very small number. Sorry, the inverse tangent of 1 is pi over 4, which is 45 degrees. So this is a lot less than 45 degrees. So when we got to 14 degrees, but remember, we're measuring it from the z-axis down. So we're rotating in terms of a declination angle. So since we're rotating here, this right here is the phi min. So that's exactly 14 or so degrees, which is just, 0.245 or so radians. Because, remember, the only reason we're doing arctan of 1/4 is because we want an exact value. Remember, an exact value is sort of better in math than it is in science, because in math, we want to leave a clear breadcrumb trail that we knew how to do the problem, whereas in science, we would just get an approximation of that. Now, by the way, even in science, we try to get the approximation at the end, not at the beginning. So we try to retain the exact values for as long as possible until, the last moment where we have to reach for them. So we're going to go from arctan of 1/4, which is just like 14 degrees or 0.245 radians, to pi over 2. And pi over 2 is 90 degrees. So that means we're going to rotate all the way down to the floor here, right?
Yeah.
So this right here is our friend, the xy plane, right? Yeah.
And if it would be of 1/8, it's going to be even more.
Correct. Correct.
And then which one would be then my other bound?
It would still be pi over 2.
It will still
as long as I mean,
as long as I'm in the
right,
XY
because the thing
plane.
is, actually, this should go down a little further. On the xy plane, in fact, let's go back to this diagram for a second. Okay? So if you consider this diagram for a second, notice that if phi goes all the way down here to the xy plane, then phi maximum is equal to pi over 2. Sorry, pi over 2 if you end on the xy plane. Right? Because think about it. If you go sort of from straight above you, the North Star, to the ground, and that's below you, like looking below you. Like imagine you're integrating down to your feet. You go from 0 to pi. But if you're going from the North Star, and then eventually you're going to end up at the horizon, you go from 0 to pi over 2. So that's why you end at the xy plane, and it's pi over 2.
To a different plane, or, well, no, xy plane, it couldn't be because...
A couple thoughts about that. I mean, I understand the question, but I need to say a couple brief things to answer that question.
Okay.
Back here, when we were doing this elliptical cone, let me just make a quick comment. And the comment is, it's assumed that the axis of the cone here is along the positive z-axis. Okay? So whenever you have the choice to set the problem up how you choose to, I would recommend using that convention. Because, think about this, most often in vector calculus, we assume that z is a function of x and y. That's the most traditional way to set things up. Now, getting back to your earlier question, could you, let's say, integrate to the xz plane? Well, sure you could. But in that case, I'm assuming the cone would have its axis of... It's the axis of the cone along the y-axis. Now, could it be done? Yes, it could. But the equation would be like the axis along the y-axis. I suppose it would be x squared over a squared plus, let me get this right, z squared over b squared minus y squared over c squared equals 0. See how I got that? So the minus goes with the y because the axis is along y.
The cone would be like this.
Right, it would sort of be sideways, yeah. Okay,
Yeah.
so,
Yeah.
I mean, some of this is just convention, you know, because we like to have functions of x and y, traditionally, right? Because we usually think of, when we first learn functions, x is the input variable, y is the output variable. But now we like to think of x and y as the two inputs and z as the output, whenever possible. So any further questions on how we got these phi bounds? Okay.
No, I'm fine.
Sure.
Thank you so
I
much
mean,
for
the
explaining that.
theta bounds are relatively easy. I mean, we're just going to go around, again, a azimuthal circle, right? So we're just going to integrate around here. So this is just 0 to 2 pi. Yeah, that's pretty easy.
Okay.
Now, in terms of rho, we have to think about this carefully. So rho is like the three-dimensional radius. So I'm thinking that here, rho min equals 0, right? Because that's just no sphere, or at least no radius of the sphere. But then out here, rho max is equal to 6. Now, by the way, you may say, well, wait a minute, what about what's going on here? Well, think about this. So, if we integrated instead from 0 to pi in terms of phi, then we'd have the whole sphere. If you integrate from 0 to pi over 2, you'd have the hemisphere. But because we're excluding this part in terms of phi, we don't need to change the rho. The rho is just still a set of constants from 0 to 6. Because if you think about it, the only thing that's done is between certain, between certain phi angles, we have to work with that. Sure.
So what we're doing is we're taking a sphere. Is that
right.
what we're doing?
So in other words, what we're doing is we're essentially deleting all of this mass. So delete. Right, just to obtain the rest of that. And again, the reason you can't just do the volume of a sphere, 4/3 pi r cubed, minus the volume of a cone, is because this is a curved top. So it wouldn't give you the exact correct answer. Okay? Now, if you didn't understand vector calculus and you wanted to just do the volume of the cone and then just whap it off here horizontally and then estimate what that cap is, it'll get you an approximate answer, but it'll be incorrect. You do want to do this formally, like so, and then you will get the full exact answer. Okay?
Yeah, I got you.
All right, so these are our bounds. 0 to 6, 0 to 2 pi, and arctan of a fourth to pi over 2 for rho, theta, phi, respectively. Don't forget, the volume element in spherical is dv is rho squared sine phi d phi d rho d theta. And remember, the order of that is sort of depending upon how you want to do it. Remember, what's the value of the integrand here if we're just doing the volume? Well, the integrand.
Oh,
right, the integrand is equal to 1 because it's sort of missing right there, right? Okay.
Yeah.
And that's just because we're looking for the volume. We're not looking for, like, what's the mass given some, density that depends upon x, y, z that you put in there, right? I think we just kind of set it up, right? And then, by the way, we can use the trick, right? Where we multiply them. Yeah. Yeah, so we can use the trick. Sorry, you had a question, though? And then I think each of these integrals is relatively straightforward, except that the cosine one's a little tricky. So the integral of d theta is just theta. 0 to 2 pi, you just get 2 pi. The integral of rho squared d rho is rho cubed over 3 from 0 to 6. 6 cubed is 216, I think. And then let's think about this last integral. So the integration of sine is negative cosine from pi over 2 to arctan of a quarter. Cosine of pi over 2 is 0. Cosine of pi over 2 is 0. So we just do minus the negative. So let me break this part down.
That's why it ends up to be
right,
positive.
that's why it's positive. Because this is negative of cosine of pi over 2 minus the cos of arctan of 1. Okay, so this right here is 0. But then negative and negative make positive. Now, by the way, when you do the cos of the arctan of 1/4, that can be accomplished by looking at a triangle like this. Because think about this. Here is a triangle that has a tangent of 1 over 4. 1 is the opposite side, and then 4 is the adjacent side. Correct? No sweat. Basic trigonometry. But it turns out that we can solve for the hypotenuse using the Pythagorean theorem. So 4 squared is 16, 1 squared is 1, and then the square root of that is the square root of 17. So do you see how I got that for r? Does that make sense? Okay.
Yep.
All right, so now that we have square root of 17, the cosine of this triangle is 4 over square root of 17. So do you see that's why they get the 4 over square root of 17 here? That comes from this term. So, again, whenever you're doing, this right here is sometimes called a compound trig problem. So when you're doing cosine of an inverse tangent, you label the triangle sides in terms of the inverse tangent, find the hypotenuse, and then find the cosine of that triangle. Does that make sense? So that's why it's 4 over square root of 17. So that's why you get 4 over square root of 17 here. And this is the answer. Notice they left the square root of 17 downstairs. They didn't really multiply it out. Again, 6 cubed is 216 times 4, and then there's a 3 down here. You could simplify that a little more if you want. There's also a 2 pi out front. You can multiply the 2 in there. Okay?
Gotcha.
All right. So, I mean, that was not easy, in my opinion, especially in terms of the cone. So I think that drawing it out here did help.
So what we saw in this problem was that we could figure it out using spherical coordinates. Made sense because we had a hemisphere, so the spherical coordinates worked best. Also, regarding the cone, a cone is going to be a constant declination angle, where the phi is a constant. Now remember, we had to come up with a phi that was not a really nice number, not a really easy to deal with angle, but we were able to figure that out. And we had to use combine trig and inverse trig to actually figure out evaluating the cosine at the end of the problem, but we were able to get an exact answer, so we showed that exact answer in terms of pi and the square root of 17, but we were also able to show, at least visually on the video, what the approximation of that volume was. So I hope that makes sense, and I hope that this has helped you. Let us know in the comments how you're going to use this in your life, in your work, in your business, in your classes, and otherwise. And thank you for watching High Peak Education. Please smash that like button as you enjoy this content. Please share this content out with your social networks to grow the channel. We've got lots of links to help you, including chapters, to navigate these videos. We look forward to seeing you in the next video. Let us know what else you want to cover on this channel.